Nash equilibrium is when two people in a game don't want to deviate from the box that they share on the matrix. So if both player A and player B go to the movies, their point allocation is -1. However, say that player A wants to go from the movies to the club. Their point allocation increases to 1, and also, if player B decides to go from movies to the club, their point allocation increases to 1 as well. And so because player A and player B have more favorable boxes that they want to go to, this top left box is not at Nash equilibrium. And so let's consider the top right box. So this is when player B goes to the movies and player A goes to the club. And so player A will have a point allocation of 1 and player B will have a point allocation of 0. But say that player A wants to go from the club to the movies. Their point allocation goes from 1 to -1, and so they don't have an incentive to move. What about person B? So if person B goes from the movies to the club, they go from a point allocation of 0 to -5. And so person B also doesn't have an incentive to move. And so this top right box is at Nash equilibrium. And if we consider the bottom left box, we also consider if player A and B want to move from this box to the top left or the bottom right. And so if the person B wants to change their mind and go from the club to the movies, their point allocation goes from 1 to -1, which is not an improvement. And if person A wants to go from the movies to the club, their point allocation moves from 0 to -5, which is not favorable. And so neither people want to deviate from this bottom left box. And so this is at Nash equilibrium. And so we consider this last box where person B and person A both go to the club and have a point allocation of -5. If person B changes their mind and goes from the club to the movies, their point allocation goes from -5 to 0, which is favorable. And so we have to consider if person A changes their mind and goes from the club to the movies. Their point allocation goes from -5 to 0, which is favorable. And so this box is not at Nash equilibrium.
Dominant strategy is the best outcome regardless of what other players decide to do. In Prisoner's Dilemma, the prisoners have two options, to confess or not confess. If prisoner B confesses, prisoner A has two options, to confess or not confess. If they confess, they'll have a point allocation of -8, but if they don't confess, they'll have a point allocation of -10. It is optimal for prisoner A to confess when prisoner B confesses. If prisoner B doesn't confess, prisoner A has an option of confessing with a point allocation of 0 or to not confess with a point allocation of -1. Regardless of what prisoner B does, it is optimal for prisoner A to confess. Regarding prisoner B, if prisoner A confesses, they have two options, to confess or not confess. If prisoner A confesses, they'll have a point allocation of -8 if they confess, or -10 if they don't confess. So it is optimal if they confess, because -8 is greater than -10.